Welcome back to G Fun Facts Online. Today we are leaving the comfort of our blue planet and drifting out into the silence of the asteroid belt. For a long time, humanity looked up at the night sky and viewed asteroids as the vermin of the skies. We saw them as nothing more than dead, menacing debris left over from the solar system's formation, rocks that served no purpose other than occasionally threatening to crash into us. But a revolution has taken place in planetary science. We now know that this grim view was completely wrong. Specifically, when we look at carbonaceous asteroids, those dark, carbon-rich rocks drifting between Mars and Jupiter, we aren't looking at dead debris. We are looking at dormant chemical factories. We are looking at the cosmic kitchens, where the ingredients for life were brewed long before Earth was even cool enough to hold a drop of water. In this episode, we are going to conduct a deep dive into the prebiotic chemistry of these asteroids. We are going to open up these rocks, chemically speaking, to see what is inside, explain exactly how a frozen rock can cook up complex biology, and discuss what this means for the origins of life on Earth. This is a story about how the blueprint of you and me wasn't a miracle on Earth, but a standard manufacturing process of the cosmos. Let's begin with the inventory. What exactly is inside these rocks? To understand this, we have to look at carbonaceous chondrites, which are meteorites that have fallen to Earth from these asteroids. These are time capsules, frozen at the moment of their birth 4.5 billion years ago. The most famous of these is the Murchison meteorite, which fell in Australia in 1969. When scientists cracked this rock open, they didn't just find iron and silica. They found a cornucopia of organic complexity that rivals a university chemistry lab. The most striking discovery was amino acids. As many of you know, amino acids are the monomers, the building blocks, that link together to form proteins, the workhorses of all biological life. Inside Murchison, scientists identified over 70 different types of amino acids. Now here is the crucial detail. They found the usual suspects, like glycine, alanine, and valine. These are the amino acids encoded in your DNA right now. But, and this is the smoking gun, they also found exotic cousins. They found amino acids like is-ovaline and alpha-amino isobutyric acid. Why does that matter? Because life on Earth does not use these. Their presence proves that these molecules were not contaminants from Earth bacteria that got on the rock after it landed. These molecules were forged in space. This was confirmed beyond any shadow of a doubt recently when samples from the asteroid Ryugu, returned by Japan's Hayabusa 2 mission, and asteroid Bennu, returned by NASA's OSIRIS-REx, were analyzed. These samples were sealed in space and never touched Earth's biosphere, yet they contained these same building blocks. But proteins are only half the battle. For life to begin, it needs instructions, it needs a code. In modern biology, that is, DNA and RNA. In a landmark finding published in 2023, scientists analyzing the pristine Ryugu samples detected uracil. Uracil is one of the 4 key nucleobases of RNA. Finding uracil is a massive deal because it supports the RNA world hypothesis, the idea that early life used RNA for both genetic storage and as a chemical tool. It turns out the letters of that genetic code were already written in the solar nebula, and you cannot build RNA without a backbone, which is made of sugar. In 2019, researchers finally detected ribose, the R in RNA, in carbonaceous meteorites. This was surprising because sugars are notoriously fragile. They fall apart easily in heat. Finding them preserved means there was a mechanism to both synthesize them and protect them. The samples from asteroid Bennu expanded this even further, showing evidence of bioessential sugars like glucose. It seems the sugar coating of the early Earth was dusted from the cosmos. Perhaps the most surprising addition to this inventory is vitamins. In the Ryugu samples, scientists found niacin, also known as vitamin B3. This is a critical cofactor in metabolism. It helps enzymes drive reactions. This implies that these asteroids weren't just providing bricks. They were providing the construction workers too, the metabolic helpers needed to get chemistry moving. And finally, in a very recent surprise from asteroid Bennu, scientists found something they informally dubbed space plastic. It is a gum-like organic polymer, a complex hydrocarbon network. While it isn't plastic in the artificial sense, these polymers act as a protective matrix, likely shielding those delicate sugars and vitamins from the harsh radiation of space. So we have an inventory: amino acids, genetic letters, sugars, vitamins, and protective polymers. The big question is, how? How do you cook complex organic soup in the freezing, radiation-blasted vacuum of space? The answer is that these rocks weren't always frozen. The secret ingredient is water. We tend to think of asteroids as dry, but billions of years ago, shortly after they formed, they were wet. They contained radioactive elements, specifically aluminium-26. As this element decayed, it released heat, enough heat to melt the ice trapped inside the rock. For millions of years, the interior of an asteroid, like the parent of Ryugu, was a warm, muddy sludge. This created a vast hydrothermal system. This process is called aqueous alteration, and it is the engine of prebiotic chemistry. Water acts as the great solvent. It allowed simple molecules, like formaldehyde and ammonia, which were frozen in the original ice, to mix, react, and transform. Let's get into the specific chemical reactions because they are elegant. How do you get from simple ammonia to a complex amino acid? The primary pathway operating in these wet asteroid interiors is believed to be the Strecker synthesis. It is a three-part recipe. You take hydrogen cyanide, ammonia, and an aldehyde. In the presence of that warm water, these react to form an intermediate called an amino nitrile. That intermediate is then hydrolyzed by the water to form an alpha amino acid. It is a beautiful, efficient reaction. The raw materials were in the ice, and the asteroid provided the warm water reactor. For sugars, the leading theory is the Formose reaction. This starts with formaldehyde, a very common molecule in space. Under alkaline conditions, meaning high pH, formaldehyde molecules begin to link together in a chain. Two formaldehydes make a simple sugar. Add another, and you get a 3-carbon sugar. Keep going, and you eventually build up to 5-carbon sugars like ribose. The mineralogy of asteroid Bennu specifically indicates it had an alkaline environment in the past, perfect for driving this sugar-making engine. But what about the greasy stuff, the lipids needed to make cell membranes? For that, the asteroids likely used a natural version of the industrial Fischer-Tropsch process. When water reacts with iron-rich rocks, it releases hydrogen gas in a process called serpentinization. This hydrogen reacts with carbon monoxide on the surface of mineral catalysts to forge long hydrocarbon chains. These are the precursors to fatty acids, the walls of the first cells. Now, you can't cook a gourmet meal without pots and pans. In this cosmic kitchen, the cookware is the minerals. If you just mix organics in water, you often get a useless tar. You need something to organize the chemistry. This is where phyllosilicates, or clays, come in. These clays are everywhere in carbonaceous asteroids. They consist of microscopic sheets stacked on top of each other. The space between these sheets is nanometers wide. Organic molecules get sucked into these tiny spaces like water into a sponge. This concentrates the reactants, making them millions of times more likely to collide and react. The clay also protects delicate molecules from breaking down. Another key player is magnetite, a magnetic iron oxide. Magnetite surfaces are chemically active and can facilitate the transfer of electrons. Some models suggest magnetite played a key role in converting inert nitrogen gas into ammonia, a form that biology can actually use. It is essentially a natural fertilizer factory inside the rock. We also see iron-nickel sulfides, which are central to the metabolism-first theories of life, capable of catalyzing the synthesis of vital metabolic molecules like acetyl-CoA. There is one mystery in this chemistry that is deeper than the rest, and that is the mystery of the left hand. This is the puzzle of homochirality. Many organic molecules, like amino acids, are chiral, meaning they come in two shapes, left-handed and right-handed. They are mirror images of each other. If you make amino acids in a beaker in a lab, you get a 50-50 mixture, but life on Earth is incredibly picky. We use only left-handed amino acids for proteins and only right-handed sugars for DNA. For a long time, we thought this selection happened on Earth. But when scientists analyzed the Murchison meteorite with extreme precision, they found a shock. Some amino acids, like is-ovaline, showed a slight excess of the left-handed form, up to 18% more. This implies that the preference for left-handedness was determined before life even started. The leading theory is that this happened in the nebula where our solar system was born. Radiation from massive stars, specifically circularly polarized light, might have preferentially destroyed the right-handed molecules in the dust clouds, leaving behind a surplus of left-handed ones. When these were incorporated into the asteroids, the aqueous alteration amplified this bias. We are left-handed because the light of a dying star told us to be. So we have these factories floating in space, full of amino acids, sugars, and lipids. How did they get here? How did they get into the prebiotic soup of Earth? The answer is likely the late heavy bombardment. About 4 billion years ago, the orbits of Jupiter and Saturn shifted, destabilizing the asteroid belt. This sent a deluge of rocks raining down on the inner solar system. Billions of tons of carbonaceous material struck the early Earth. While big impacts vaporize everything, smaller rocks and cosmic dust can land softly. This delivery system solved a huge problem for the origin of life. The early Earth's atmosphere was likely dominated by carbon dioxide and nitrogen. Making amino acids from scratch in that kind of atmosphere is very difficult. But carbonaceous asteroids acted as a supply chain. They brought the hard-to-make compounds, the ribose, the vitamins, the complex amino acids, and dumped them directly into the primitive oceans. Because these meteorites are porous, when they landed in shallow pools, they acted as concentrated nutrient pills, leaking a rich chemical slurry into the water. Everything I have told you so far was a theory built on meteorites that sat in museums for decades. But we are now living in the golden age of asteroid exploration. We have the ground truth thanks to sample return missions. JAXA's Hayabusa 2 mission brought back samples from Ryugu that were pitch black, resembling charcoal, and incredibly porous. The analysis showed the parent body was once 97% water-altered minerals. It was essentially a ball of mud. The samples contained tiny clumps called dark inclusions that were even richer in organics, suggesting complex generations of processing. Then came NASA's OSIRIS-REx, which returned a massive haul from asteroid Bennu. Aside from the space plastic I mentioned earlier, Bennu was found to be rich in pre-solar grains. These are microscopic diamonds and silicon carbide crystals that formed around other stars before our Sun even existed. They traveled through interstellar space, got trapped in the asteroid, and survived billions of years to tell us their story. The Bennu samples also showed great diversity. Different pebbles had different chemistries, proving that these asteroids were dynamic worlds with different geological zones. The implications of this extend far beyond Earth. If asteroids delivered these ingredients here, they delivered them to Mars too. Mars might still preserve these ancient rocks on its surface. Furthermore, the chemistry found in these asteroids, the aqueous alteration of rock, is exactly what we believe is happening right now on the seafloors of icy moons like Europa and Enceladus. The mudball phase of Ryugu is a frozen snapshot of the active hydrothermal vents on those moons. If Ryugu could make uracil and niacin, Enceladus likely can too. This brings us to our conclusion. The most profound takeaway from the study of prebiotic chemistry on asteroids is the resilience of life's ingredients. We found these molecules on airless rocks, exposed to the hard vacuum for 4 billion years. We found them forged in the cold dark. This suggests that the chemistry of life is not a fragile one-in-a-trillion accident. It is a sturdy, industrial process that happens on wet rocks everywhere in the universe. Wherever there is carbon, water, and heat, the universe makes amino acids. It makes sugars. It makes the building blocks. The Lego kit of life is standard issue in the cosmos. We often look at the stars and feel small. But the story of carbonaceous asteroids tells us that we are intimately connected to that vastness. The nitrogen in our DNA, the calcium in our teeth, and the iron in our blood were forged in stars. But the molecules, the specific arrangement of atoms that allows us to live and think, may well have been forged in the dark, wet belly of a passing asteroid. These humble, charcoal black rocks are the bridges between the astrophysical and the biological. They are the vessels that carried the fire of life across the cold desert of space. As we study the grains of Ryugu and Bennu, we are reading the opening chapter of our own autobiography. Thanks for listening to G Fun Facts Online, and remember, look up, you are looking at your history.